Hi, my name is Schoelkopf, and I'm going to be talking about an environmental engineering application of 3D printing. Before we get started, I wanted to talk a little bit about stream tables. So I decided to 3D print hydraulic structures to put into stream tables. If you're not familiar with them, stream table has a reservoir of water underneath of the sandbox style thing you can see in the pictures here. The water is pumped up with a water pump, and then the water flows down through the media and simulates and models rivers. The way that people use these are for sediment transport, geomorphology, dam simulations, fish passage, hydraulic structures, hydrology such as groundwater flow, flooding events, and also for soil science like soil conservation. All right, we'll jump into the purpose of the design goals. So my main purpose was to apply 3D printing to environmental engineering. The way I did this was by 3D printing hydraulic structures for stream tables and ultimately flumes. Environmental Engineering Society allowed me access to the stream table, so I used that stream table to implement hydraulic structures. We also use that stream table to travel around and educate people about geomorphology, hydraulic structures, hydrology, and soil science. So for the design goals, I wanted to recreate and improve previously subtraction manufactured hydraulic structures. They were actually very expensive. A set of 3 acrylic weirs was actually $100, so I thought they would be very easy to drive this price down, and by making my creativity relatively free by using additive manufacturing, I was able to print an array of hydraulic structures that I thought would work really well for conveying the information that I wanted to, and not just what was on the market. And again, the price was a lot cheaper. So we'll talk a little bit about the form, the fit, and the function. I have about 6 different structures that I printed, so I'll try not to go over too much time with this. So the first structure that I'll talk about is the earthen dam. I 3D printed this because I wanted to show soil conservation, but at the same time I wanted to show how subsurface flow can still go on even if you're trying to conserve soil. I did this by showing how water could move through the media in the stream table and through this block structure or an earthen dam that has hole slots in it so that water and subsurface flow can still move through it. The next structure is the bridge. I wanted to show kind of a classic hydraulic structure that you would put into a river or an ocean or a lake or something like that. And a bridge is a classic example. There's always degradation and aggradation issues that go on with hydraulic structures, and bridges are very easy to see with that. And also I wanted to kind of convey how maintenancing and proper armoring of these bridges when you put them into a river or next to a stream or something similar to this, or maybe through a marsh, that it's very important to know what you're going to maintenance, how you're going to maintenance it, and if it's going to be maintenanceable when it needs maintenance, and also that, like I said, proper armoring if you need to, if you have a lot of degradation around the bridge. And what I like to focus on with all of these hydraulic structures is just the downstream effects of putting them in the river. There's always an effect. The velocity will change, and the pressure on the bridge will change the way the stream power moves. Yeah, so I modeled and made this 3-piece culvert that shows 3 different diameters of culverts. And if you could look to the left, there's these equations that Manning developed that describe partially full pipe flow parameters. And we use these to show how to size culverts and how to make the correct calculations when using culverts. And we also use this to show external sources of water coming into a river and how that affects that downstream position from where the water is entering. And again, with every one of these hydraulic structures, it's proper placement. You got to make sure that you're not affecting the health of the river. You have to understand the geomorphology of what's going on, and we can do this simply in a stream table. The next one is a tincture gate. This thing moves radially, as you can see in the schematic to the right. It's used for locks and canals. It'll adjust the water surface elevation if a boat needs to come in or leave. And it really has a huge decrease on the stress of the structure. That's why they have the radial structure. That's why they're so prevalent in lock and canal technology today. But they can also be used for fish passage as well. And the one to the left is clearly the one that I 3D printed, and it worked very well. The middle peg kind of broke when I was trying to set it up for a picture, so here's the two pieces. But it worked very well when I had it in there, and it actually works without the center rod as well because it's not able to be mechanically moved or moved by the flow due to the high friction between the two pieces. So here's a couple other structures that I printed. To the right is a topographic map. That's a section of Yosemite National Park. And I actually decided that this was kind of outside the scope of the project. It was going to take roughly about 3 kilograms of material, and that was just a lot for me, but I'm just going to keep building it on my free time. I have about 8 of the pieces done out of 21. So to the left is just a basic dam structure that I used to make it a solid structure to ensure that we get a lake forming or a reservoir or a dam if that's what we're going for. But it's more of just a structure underneath the soil surface. Then this Syrian dam, I found this one on Thingiverse. Someone had modeled the Syrian dam, and so I decided to print a little small model of that and put it in, and so there it is. So highlights, stuff that I thought went very well. I applied this actually after I used them, or after I printed them, and I used them at the EES barbecue, and it was so easy to teach the concepts. It was great to have the visual aids to show how the calculations would work or why you would want to use specific calculations, in particular the sizing of the culvert. And then you also just get a nice systems engineering or river engineering / management view by using these stream tables and hydraulic structures, and not to mention how cheap it was. I would rather pay 20-25 bucks for some ESUN PLA and get 9 hydraulic structures out of it than pay $100 for 2 or 3 hydraulic structures that are made out of acrylic that quite frankly weren't very accurate. Right. So we're going to talk about some things that I learned from this. So the mistakes that I made were not accounting for the hydraulic structures being hollow. A lot of them floated, like the Syrian dam. I had to weigh it down with a couple of rocks or something like that. I guess the assumptions I needed to make were that friction in between the parts is not going to be accurate. A lot of these things use like large bearings or other ways of moving these pieces, and so I didn't account for that. With the Syrian dam, the only way that flow can move through it is at the critical capacity, and that's not realistic either. We would like a base flow that could flow underneath it, would be ideal. I also didn't really account for the foundation of the bridge. There is really no foundation of the bridge. It's just kind of sticks that poke into the sand, so we had to armor that very heavily, but you would normally have concrete that you would put into the ground, and you would make an entire structure that would support the bridge. The roughness of the culverts, I printed the tubes vertically, so when the slices were printing, it's very rough on the inside of the tubes because of the way that I printed them. I'd need to look into seeing kind of how that affects the way that we calculate the other factors of the pipe. And just overall scaling of the models, I didn't think very much about the scale. They all fit within the sandbox, or within the stream table, excuse me, but some of them are very large, some of them are smaller, especially the Syrian dam is very small, and the sediment size would almost be boulders in comparison to the Syrian dam. And yeah, also the sediment size, being able to have like a varying sediment size so that it's a little bit more of a realistic simulation would be nice too. So what I would do differently with the hollow issue, I would either drop weights in there while it's printing so that it can weigh it down, or maybe make them mountable, have clips or some other structure that I can attach to the stream table so that I can attach the hydraulic structures. So far as the assumptions with the friction, I mean, I could maybe try to put bearings in, maybe smooth it with acetone, but that just seems a little too excessive, and especially outside of the scope of this project. For the Syrian dam, maybe drilling a hole through the center or being more acquainted with 3D software. This is my first time using 3D software, and so it's gone pretty well. And like I was saying, the roughness of the culverts, maybe look into figuring out how to make exact roughnesses inside the pipes. And I'm also going to start printing with ChromaStrand. I printed various other things not related to the stream table, and I used ChromaStrand. It's just very strong, very reliable, great detail. So I'm going to start using that. A little more expensive, but I like it a lot, and it prints very, very reliably. And main point I'm going to do is focus on the scale of these objects, and if I have multiple things in one river, I need to make sure that they're all kind of operating on the same scale. Thank you for your time.